Okay, this is going to be more of kind of a show and tell than a talk. I just want to explain how this works, what we use it for, that sort of thing. So I think kind of the goal of this workshop is you want to understand this machine here called the D-dia, how it works, and how you can apply it in your own research. So has anybody ever used the D-dia? Does anybody recognize this thing? No? What about X-ray diffraction? Okay, so a bit of diffraction. So we use this thing to generate high pressure and temperature, and then deform a rock under those conditions, and then we collect diffraction and radiographs of our sample. So this is just showing pressure versus temperature for a few different apparatuses. So you have gas apparatuses, they're very electrostatic, but they can't generate all that high of pressure. Piston cylinders are somewhat similar to this device, but they operate at somewhat lower pressure too. And then the D-dia, we can sort of reach this region. I don't know, this is actually kind of optimistic, about 7 GPa, probably more around 10 is sort of working operation, but you can push it higher to that under certain circumstances. And then you can get up to around 2000 Kelvin. So, and this is just kind of a picture of the setup. So here is these anvils, which are going to go in there, which will show you how. You have a pressure cell at the center. And if you cut away the pressure cell, you have these little components, and then you have your sample at the center. And the samples are on the order of maybe 1 to 3 millimeters kind of thing. You can go bigger than that in some applications, but 1 to 3 millimeters is so large that they refer to this as a large volume press, even though it's kind of small. And as I mentioned, you can collect diffraction and radiographs in situ. So basically you have this apparatus here, and then you have these anvils. So this one here is made of sintered diamonds. And the reason we use that is that it's transparent to X-rays. So on the backside, you have your synchrotron coming into this pressure cell, and then you have a diffractive beam coming out. And the diffractive beam will have to go through these anvils. So we use diamond instead of tungsten carbide. I'll actually go backwards a bit and start talking about the pressure cells. Or actually, I should talk about the sizes first. So you'll probably want to also like get up and come up here and look at this.
Yeah.
We have a bunch of different anvils.
Feel free to come over and take a look.
Yeah. And I can
raise your hand.
So this isn't like a talk. It's just sort of explaining. You see how you see these different anvils, how they all have different sizes on the end. So this one's 12 millimeters, this one's 3 millimeters, and so on and so forth. And we have all different sizes. So you see these kind of triangle things. You see how there's a bunch of different sizes of these on the ends. So since pressure is force divided by the area, in order to generate a lot of pressure, you can increase the force, but you can also minimize the area. So the smaller we go with everything, so here's our pressure cells here. This is a really big one. Here's some smaller ones. So this is for the 3 millimeter truncations. This is for 6. This was for like 20. It was actually for not a different experiment in here. But you can see the benefit of going bigger is one, it's just bigger. It's a lot easier to manipulate if you want to put wires in and all sorts of other things. And also you can use larger, more complex rocks because the actual physical size of your rock can be important in certain applications. So you take, ultimately what you want to do is your sample will be at the center of this cell here. And then you'll have all these other components that go in around it. And the purpose is we want to generate high pressure and temperature in our sample. So what we do is we have the sample at the center, and then we have these small parts that go in. So these little black cylinders here, those are a furnace. So we can run a current through it and generate high temperature. So this like black cylinder will be inserted into this hole in the cell. So you have this black cylinder here, it goes in the hole and it goes down here. And then we run a current through the anvil, through this furnace. And when we run a current through this graphite furnace here, it'll heat up. So that's how we heat up our cells. And then on either side, we have these pieces of Al2O3. You see these little pucks. So these little things here, they go on either side of the sample. These are Al2O3. It's dense and it's hard. So when we start pushing on it, we can deform the thing easily. And then we have some other, this is also Al2O3, but it's porous. So as we compress it, it's gonna, get crushed and take up its porosity. So once you have your petrol cell and you've loaded everything in it, you want to load it into the press. So basically, you would take it and you would put it on this anvil here. Oh, there it is. You wouldn't put it on this way. The furnace should be facing upward. Your hole. And then you'll put in these anvils down like this. So you see how now you have this anvil face, this truncation fell off, but it's going to be touching the cube. Mm-hmm. And there's 4 of these that are going to go around the outside. Mm-hmm. And then you have one on the top and one on the bottom. So you have your pressure cell, which is a cube. And then you have 6 anvils pushing on the face of the pressure cell. And what happens, because of the geometry of this thing, you see how it's like kind of like a triangle face here? Well, this is sort of, it's the opposite. So it's going to be holding it like that. So what we do is we put this, we'll like close it up, and then we'll put it in a hydraulic press. And underneath this, there's a ram that's going to come up. And it's just going to push this together. So it's going to push it down on our cell. And because of the geometry of this, it fits in the D-dia like this. So as we close this, it moves forward. So then it compresses the cell. So we have our 6 sides all getting compressed, and that's going to increase the pressure. And what happens to the cell is, oh yeah, it's still in. So our cell, actually, I'll use this one because it's the smaller one. So we have our little small cell here. We're pushing on it from all 6 sides. And what happens, this is just made of basically powder that was glued together. But once we put all this force on it, it's just going to break up and then it's going to flow in between the anvils. So you see how this one, you see how it has these like fins coming out of each side, like each edge of the cube. You see these like fins? So originally it was like this, but now it has these fins coming out. Those are gaskets that are in between the anvils. And so the anvils won't touch each other, and they're going to hold all the pressure inside our cells. So you have these little tiny, it's not that tiny, but a few hundred microns gap in between the anvils. So you'll have two anvils that are, imagine the synchrotron beams coming towards me, and they're like this. And then this gap between those two anvils is where the synchrotron beam enters. Okay, so then you have that. It comes in here in this gap between the anvils, which is those fins that we're generating from the pressure. And then it's going to diffract out the sample. And we can also, we have a camera and a scintillator, so it can move into the beam. And then we'll take a radiograph. I think I might have. Okay, well, I'll talk about this first. So the whole point is, I didn't realize this was a movie. So I talked about this. So we have our anvils, we have our cell at the center, synchrotron beam coming in. We have diffraction, and we can also collect images. But the neat thing about the D-dia is that we also have, so there's a ram underneath this, which is pressing the whole thing closed. And because of the geometry, we're transforming our 1D force into forces in 3 directions. But then once we're under high pressure, and that's supposed to compress it relatively hydrostatically. So your sample is hopefully hydrostatically sitting there at high pressure. We can run a current through it, we heat it up. But what's interesting about the D-diet is we can deform the rock while it's under high pressure. So this here, these valves are to connect separate pressure lines. So now while it's under pressure, we can pump oil through these lines and pressurize the bottom and the top ambulls, and we can force them forward while we're under pressure. So that's the way we deform our sample. So here's a picture of that. So to measure how much strain we have in the sample, so the strain is when a material changes shape. So we have our cylinder, bring it up to high pressure and temperature, and then we push on it harder in one direction, and it's going to strain in that direction. So here, the sample is actually wider than this. So this is the sample. We have our dense Al2O3 pistons on either side of it, and we're going to push it from the top and the bottom, and it's going to get shorter, and we're going to measure that length using the synchrotron. So on the ends here, we put some gold or platinum foil or something really absorbent so that we can see an edge to the length of our sample. And then this is a movie. So we're just collecting radiographs, just like you'd get an X-ray. Different materials are going to absorb stuff differently. So the sample will have a different absorption than the pistons. And then we have these really absorbent material on the edges. And then we're just going to measure how long the sample is as we're pushing on it. So you see it's getting shorter because we're pushing on it from the top and the bottom while it's under high pressure. I think too, you can't really see here, but the sample cracked, which we were trying to do.
Question. Both of them moving at the same time.
They are.
There's no fixed one being on a fixed position.
They're not in a fixed position, so they both can move. Yeah. You could just move one and deform it, but you could double the amount of force you put in, and it keeps everything centralized. So we use both at the same time. Let's see. So in order to collect our radiographs, we have this scintillator and a camera in place. So this scintillator thing, all it does is when it gets hit by a photon, by an X-ray photon, it generates an optical photon that can get picked up by our camera. So basically the X-rays that come through here are just going to form a picture on this scintillator thing, and then the scintillator thing is going to be fed in the camera. But one of the nice things about it is that we're focusing on the scintillator, not on the sample. So we could move this around and it wouldn't change our image at all. We don't have to refocus. We just focus once onto the scintillator, and then we're good to go to collect radiographs. However, I think the next slide's diffraction. So we move these two things into the beam path and take our picture. And then when we want to collect the diffraction pattern, we move them out of the way. Oh, that's just maybe. And then we can collect diffraction when they're out of the way. So all our ambuls will be pushing on it. The beam comes in through that gap, and you get a diffracted image coming out the back. So at this beam line, 13 VMD, we do mono beam diffraction. So we only send in one X-ray energy. At sector 6, they do energy dispersive diffraction, and they send in all the energies that the synchrotron produces, but we only use one single energy. So Bragg's law here, this lambda, the wavelength of our X-rays, is fixed. And then, so imagine these are two crystallographic planes, and you have X-rays coming in, and they scatter off the top plane, and then you have another X-ray that comes in and scatters off the bottom plane. This distance here is the extra distance that this one travels compared to this one. And if this extra distance, so this is theta in here. So d sine theta is this distance. If this distance plus this distance, 2d sine theta, if that equals a wavelength, then these two X-rays are going to constructively interfere with one another. So only like a plane with this specific d spacing is going to generate constructive interference and a diffraction peak. So by looking at the position that our diffraction peaks show up, we can measure d here. We can measure the distance between the crystallographic planes, and that's very useful to us. That's sort of what diffraction does. Now we're doing powder diffraction, and I realize I have these little toys. I'm going to shoot X-rays down there, so you might either get out of the way or they should be above your head.
Sector may not be big enough.
So here's our sample, and this one has 500 lines per millimeter. And we shoot our X-ray beam through it. So you see this, the one in the center is just coming straight from the laser, but you see the two dots on the side? Those are diffracting off this diffraction grating here, which is just a bunch of slits. So it's similar to just a bunch of planes in a crystal. Now, this one has 500 lines per millimeter. This one has 1,000. And if we look at, so this is 500, and now here's 1,000. You see how they come out at a bigger angles? They're further away. So the more closely the lines are spaced, the smaller this D value, the wider the angle they diffract. So they actually call the diffracted stuff, they say it's reciprocal space. So if stuff gets small in real space, like our crystal gets smaller because we're pushing on it, then in reciprocal space, the angle will get wider. Now, what we do is we have, what's it called? And it will depend on the energy as well. I don't know if this is, so this one's red, and you can see they show up sort of there. And then if we use green, they show up a little closer in. But we can choose whatever energy we want to run our experiment. So if we use higher energies, it'll sort of squeeze this diffraction pattern in. We'll be able to get more peaks and go out further. But if we use lower energy, it'll stretch this out and we'll have higher resolution for our peaks. So I should say, what happens is we're doing powder diffraction. So we don't actually use powder, we use like sintered rocks. But they're made of powder originally. So think of, you have like 1,000 grains that are in your diffractive beam path. So imagine you have a grain. So these lines are going up and down, and it's like this, and you get your spots, like the two that are on the outside there, you get your two spots. But now you have a grain that's oriented this way, and your spots are going to be up and down. And then you'll have a grain that's oriented this way, and another one that's this way, and so on and so forth. And you have so many grains that you feel, they're all coming out at the same angle though. So if I rotate this, it's like rotating it around a circle. I apologize if I just blinded somebody. But anyway, so if you have tons of grains, they just fill up this whole ring. They're all coming out at the same angle. So they're going to be all the same radius away from the center for a specific like crystallographic plane distance. And then you'll fill up the whole circle because you have a bunch of randomly oriented grains. Does everybody follow that? Yes. Does anyone not follow that? Okay. So if you take, let's do it this way. So we have our crystal, and you see the spots on the side. Those are where the diffraction patterns show up. So the laser's coming in, and then it's coming off at an angle to make a dot at that position. But now you'll have another grain at a different orientation, and it'll make a dot. You see that the outer dots, as I rotate it, they spin around, but they stay the same distance away from the center. You see what I'm saying? So then you're basically filling up the whole circle from a bunch of different grains of the bracket. So you'll get a diffraction peak at a particular position. And then, of course, the crystals are going to have more than just one crystallographic plane. They got a bunch. So you're going to get a bunch of circles. And then if you just add up around the circle where they're all the same radius, you can get the single 1D diffraction pattern, like you're probably perhaps more familiar with. When you put stress on it, you start to get these squiggles. We'll talk about that in a second. But okay, so that means you need enough grains to fill up the whole circle. So if you look at the picture on the left, there's not a whole lot of grains within the beam path because each grain will just like produce a dot. And if you have enough of them that are randomly oriented, you'll fill up the whole circle. But this one doesn't really have that many. So you're mostly just seeing a bunch of dots. This one you have like more, but you can still see their spaces. So you have to have small enough grains that you can fit them into the diffraction volume, or like fit them into the synchrotron beam so that you can fill up this whole circle. Because the type of analysis, which we'll talk about a lot over the next 2 days, you need to have this circle filled up to be able to do it, or at least reasonably filled up. This one would be pretty hard to do. This one would probably be fine. And then here we just have like smaller grains and we have perfectly filled in full circles. One thing that happens though, when you pressurize it, and particularly when you heat it up, these single dots become smeared out, and you basically, even this sample, by the time you're deforming it at a high pressure and temperature, it will actually fill out enough of this ring that you can do the analysis. But if you only had just like 1 or 2 dots, you wouldn't be able to do it. Should I talk about the squiggles now? I guess I could. So what happens is, so as we, I think I have actual, how long have I been talking for? Probably a while.
I have no idea. I think
Anybody
it's
check
10,
when it started?
I think you've been talking for like 20,
Oh, that's it?
30,
Okay, good.
30 minutes.
Okay, that's fine then.
We started at 10:20, right?
I think so.
Yeah.
Okay, so
You can also end where you want.
I think I'm just gonna end when I run out of time, probably. I'm not really giving a talk, I'm just talking.
You have at least 15 minutes.
At least 15? Oh,
Or you can ask questions.
that's not nearly enough. But anyways, over time, basically, we're just going to like what I'm explaining now, we're just going to explain that to you over and over and over again over the next couple days so that you understand how to run experiments. So when you have so you know what its capability is, and then you'll have an idea and you'll come here and you'll run an experiment, because everything that you see here, you're allowed to use. So here's our original diffraction pattern at just 0 pressure. So you'll want to calibrate the distance of the detector before you start your experiments, because you know what angles the diffracted thing should be coming out at, but you don't know how far away your detector is. So if you look at my thing here, so depending on where the so right there's my, this will be my spot.
It's your 0, 0, 0.
Right? And then as I move closer, obviously, they're going to show up at different positions, but this angle is always preserved. So they come out at a certain angle, and then we measure using diffraction, we'll measure the distance to the detector and consider that fixed for our experiment. So that's the first thing you do before you pressurize anything, because once you start pressurizing things, then the despacings are going to get smaller. So here is this mineral, it's phaolite at 0 pressure. And we have our diffraction peak is right on top. Another thing that's useful is do you know how to get rid of the like zoom, like pause and share and stuff like that? Can you do that while you're sharing?
I'm sure you can.
And,
Might be able to move it, but.
Um,
What do you
Any-
want to do?
like, just you see all this like stop share and stuff and
Like, we don't see that, you know.
yeah, I know you don't, but
You see, like. Others you.
okay, so this is what our image actually looks like. It's the circles. But sometimes what we want to do is we want to, since they always have like the same radius, we'll plot it with the angle on the y-axis versus the distance. So this distance here is 2 theta. So if we do that, it's kind of like unwrapping that circle. So now we have the angle around our circle versus the radius of our circle. And because the sample is just, it's not under any pressure or anything like that, these will be completely straight lines because there's no, actually, why don't I just show you when they start to get stressed. So now I don't really know what's going, this is a different material, but now we're sort of increasing the pressure. And now you see this line's moving out, it's moving further. So it's going to a bigger angle because we're bringing the crystallographic planes closer together because we're squishing it. So the planes get closer together in reciprocal space. That means the dots get further apart. So now you can see that this, which was originally right on top of this line here, has moved to higher 2 theta values. So it's a bigger angle. And we can measure what the pressure is if we know the equation of state, which is something that relates pressure, temperature, and volume. And so if we increase this, we're still at room temperature. So this is at 0.7 GPa. So we can measure the pressure directly in situ using the synchrotron. Now, whoa, okay, so now we have a lot of stress. So now these things got warped. They're no longer straight. So what happened is, let's say you have a crystal that's oriented this way, and a crystal whose planes are oriented that way. The beam comes in, it diffracts off these ones, and it gives us a point here. And then we'll have one that's like this way. Gives us a point here. But when we deform the mineral, so we're under high pressure, we've squished it, and now we're driving our top and bottom rams to deform it in one direction. These planes here, they're going to get smaller in this direction. So these planes will be more crunched together than the planes in this direction because we're not pushing the crystallographic planes together in this direction, but we are in this direction. So what happens is these ones will actually get a little bit wider that are perpendicular. So it'll diffract out here. But this one, now that the planes are closer together, the crystals that are oriented this way will diffract, say here. Because they're closer, it'll diffract at a wider angle and they'll come out higher. And then the grains that are in between will be somewhere intermediate. So what originally was a circle has now become an ellipse. That wasn't a very good ellipse, but do people understand that concept? So we're squeezing it harder in one direction. The planes are getting closer in that direction, so they diffract more. So our circles become ellipses. And what we do is we fit this ellipse and that will tell us what the differential stress is. So we know our pressure from like how close they all are together. And then when we start to stress it, we know our the differential stress from the fraction. And you can see this one is starting to build up some stress. So if we go back to the picture, if I pick, say, this line, see if I can see. Yeah, okay, that worked. You see this line here, you see at the top, this green line is a perfect circle. But you see at the top, it's a little bit, it's not a perfect circle anymore. It's an ellipse now because we're swishing it more in the vertical direction. So it doesn't change by like a huge amount, but it'll change a little bit. So we see our ellipse, but now if we go back to the cake pattern, remember when we unwrapped this thing when there was no differential stress, and we just got a perfect circle because all of the planes are squished an equal amount in all directions, but now they're squished more in the vertical direction. So if we look at that cake plot now we see that this is 90 degrees. They're reflecting by a larger amount of tooth theta. And less so. So basically to fit the ellipse, we do it in this geometry, and you just fit this peak along this whole thing. And then from that, you'll know the pressure and the differential stress of your material. And you also know the strain, so you can generate stress strain curves. Something like this just happens to be here. Forgot to make one of these. But so here's strain on the x-axis and stress on the vertical axis. And if you plot them against one another, you'll get something that looks kind of like this. So that can't be 5% strain. I think that's should be. Then
It depends on where you define your
depends, yeah.
L0.
But anyways, so what will usually happen when you start deforming a mineral at high pressure is first, if you just started like pushing on it a bit and then let go, originally they'll just elastically rebound back to where they were. But if you push hard enough and long enough, eventually it'll yield and it'll start to deform plastically. And then eventually you'll just reach this stress saturation where you can add more, you can keep pushing, like try to push harder, but all it'll do is just strain the mineral. It won't build up any more stress within the crystal. So stress strain curves are a really big part of this device. Let me see what's in my talk. There's not a whole lot. Oh yeah. So we actually we can measure like the macroscopic strain from the plastic deformation, but we can't measure plastic deformation on like a crystallographic level. Because what plastic deformation, it's the movement of defects through the crystal. And we can't measure defects. We can just measure the distance between crystallographic planes. So here you have this like defect in the crystal, and we're able to measure this distance, right? But we can't tell what this is. And then when it's plastic, you have this defect will move through the crystal, but we can see that it's like macroscopically straining the crystal, but we can't access that information from the diffraction patterns. And then I think the last thing I should mention is that when we want to, so once it's under high pressure, we also want to heat it up. So like I said, you connect cables to the outside of this thing and you run a current through it. And when this is like closed and you're actually pushing on it, you have an anvil on the top and an anvil underneath. And then we run a current through that. I'll use the tungsten carbide. And then a current through the anvil, which then goes through our graphite furnace, which goes down through the anvil on the bottom to complete our circuit. And when we run a current through the furnace, it'll heat up and we can heat it up, 1500 degrees, kind of no problem while and then deform our mineral. But typically for deformation experiments, we don't use thermocouples. So I have an example of the thermocouple. It's just a little wire. And at this junction point, you can measure what the temperature is. But if you put this wire in your sample and then you start pushing on it, it's really easy to break it. So typically what we do instead is we run a separate experiment where we don't deform it. We heat up the sample and we measure the temperature. And then we record how much current or how much electrical power we have to put through the circuit for a given temperature. And then we'll make this calibration curve between the electrical power that we put in versus what temperature we measure. So then later on when we run our experiment and we don't have a thermocouple, we can just put in a certain amount of power and we say, well, we know at 150 watts, the temperature should be 700 degrees or whatever it is. So we use that as our calibration so that we don't have to use thermocouples in our deformation experiments. And you can see this one was at 20 tons. This one's at 40 tons. The load, so that's the main load that we're putting on the module. And you can see that it changes slightly at different loads and is more efficient at lower loads. I think just because there's still a little porosity and it doesn't transfer heat as well as it does after you keep compressing it. I think I've covered the major stuff about our experiments. Does anybody have any questions? How many of you right now,
No,
sorry,
it's okay. Is there a correction factor to kind of account for the difference?
I mean, you could come up with one. Typically, if we run a calibration experiment, although this isn't all the time, you could, if you had 25 tons, try and come up with some correction factor between these two. Usually, if I'm at 25 tons, I'll just use the one for 20. I should also mention that there's uncertainty with this setup. So your temperature could be off by 25 degrees easily. Under sort of weird strain situations, it might even be off by 100. Another thing that I should mention, if I go back to our cell design here, we have very large thermal gradients in our sample. So at the center, which is usually where we put our thermocouple for our temperature calibrations experiments, let's say it's 1,000 degrees right at the center, it might be 900 degrees a millimeter away. So we have large thermal gradients within our samples, and that it's really bad as you go up vertically. It's not so bad radially unless you go outside the furnace, then it drops off dramatically quickly. So anyways, how many people just sort of understood what I said and have a decent idea of what this thing does? Put up your hand. I won't yes, we did. Okay,
Very good.
great. So it looks like everyone at least they're telling the truth, does understand it. So that's sort of how this thing works and what we use it for.